Hello everyone, and welcome to Chapter 4 of Introducing Python. This is a bit of a long chapter. We're going to put this into two parts, and the first part's going to be a bit shorter, and it's going to cover conditionals. So these are ways in which we evaluate something as true or false, and then change the flow of the program as it goes on from, the evaluation of true or false. Then in the second half, which is slightly longer, we're going to look at iteration. So iteration is how you can do a repetitive task repeatedly or set some conditions for which Python will do something over and over again. Now there's a few different ways to do iteration, and we'll see those down below. To get a brief view of this as we go along, we can see in the table of contents here. First, we're going to use conditionals to change the flow of a program. Then we'll look at these right here, Boolean and flow, like if and else type of things. Then we're going to go into a bit of an interesting section that can trip some people up about missing values, or what happens when things evaluate to neither true nor false, or perhaps, what is an empty string? Is an empty string true or false? So we'll explore these down there. And then in the second half of this, we're going to look at iteration. We're going to use for loops and see some interesting sort of extra details with for loops, like the else condition, the enumerate function, which is something I use an awful lot, how to manage loops, and then some advanced things with loops. Here we have example of a double loop. Then we're going to look at how to iterate through dictionaries. Down here, list comprehensions, dictionary comprehensions, which are pretty similar. These are really handy, and I use those all the time. Then we'll cover while loops, which is a loop that will just continue running until you set some condition. And finally, we'll look at errors. So in addition to changing the flow of the program based on some condition, you can also stop the flow of the program or prevent the stop of the flow of a program using errors. So let's get started. So a really common way to manage the flow through a program or through an algorithm is to use conditionals. And so that's where we can evaluate something as either true or false and do something under each of those conditions. We don't tend to have a maybe condition, but we tend to use lots of if-else type statements, and you'll see those as we go along. So in life, there might be many sides to any story, but in Python, we have pretty strict conditions, and so Python will evaluate things as to being either true or false. So for example, if we have a set of things, in this case, we have a variable called characters, it's a set, and then we have Kermit, Piggy, and Fozzie in there. So if we ask if Kermit in characters, the program will return true. Also notice that true here is, to remind, an uppercase. And we can see that that's the case. Now, you might have noticed that Kermit, Piggy, and Fozzie are all names of characters from The Muppet Show. So in a sense, you can say that, a Muppet is in characters. And so that would be valid from a semantic sense, but from a programming sense, that wouldn't be accurate, because the program doesn't know that they're Muppets. It just knows that these are specific strings of data, and it evaluates whether that string of data, such as Kermit, is in that set. So the most common conditional in Python, almost certainly, is the equals comparator. We call it a comparator here, and it's two characters in a row, or two equals characters in a row. If we recall, if we use one equals character, then that's for variable assignment, whereas two is for comparisons. So see an example below of using the comparator. So first we're going to assign this variable a to be 42, and then we say print a equals 42, and that should print true. Now, if we print b equals 55, we assign it, so we'll say, does a equal b? And it shouldn't. A should equal 42, and b should equal 42. But, just to be clear here, it's not just whether b equals a, explicitly whether it represents the value 42, that's also going to be false. So, of course, we can see that there. It should be pretty straightforward, but perhaps the next one might trip people up a little bit. Now, notice what happens when we print a equals 42, but what we're doing here is we're using the variable assignment. So recall that we'll assign 42 to this variable, and so watch what happens when we print a equals 42. We get this type error here. It says a is an invalid keyword for argument print. So if you stumble upon that, well, first off, chances are you probably meant to use this right here. But it's also the case that functions have keyword arguments, and right there we can see, if we go into the help, we have some such as sep, end, file, and flush. So a is not one of these right here. If we use a equals inside a print statement, it's going to say are you a keyword argument for this? Now, if we went sep equals 42 instead, and just watch what happens when I go, the classic, hello, Terrans. And then if I put sep, what it should do is put a 42 in between each of the things that we printed. And sep must be none or a string, not an int. Oh gosh, being very strict here. But there you go. You can see how the separator works there. And if you use end, it will use whatever you put here at the end of the print statement, where the default is the new line. But the important thing here is that it's not the same as a comparator. So in the earlier chapter, we spent virtually no time on the primitive data type of true and false. And that's because I wanted to introduce it here when we talk about the flow of a program. So, of course, we just saw the equals comparator. So that's equals equals. Does x equal y? We can use and to see if two things are both true. So if x is true and y is true, then this statement right here will evaluate to true. On the other hand, if x is true or y is true, this will evaluate to true. You may briefly recall that we had a look at some sets earlier on, and so this is pretty similar to intersection, and this is pretty similar to union. Why intersection for this one? Because in this case, that means they both have to be true. So it's like you have those two circles, and it has to be whatever's in the overlap between them. On this hand, right here, why is this the same as union? Because it's like, imagine those two circles, and if there's a true in either circle, doesn't have to be in the overlap, then it will evaluate to true. So we can use not as well as bang for not or negation. So imagine if x is some value, and this will evaluate to whatever is the opposite of that. So if x is true, it'll evaluate to false. If x is false, not x will evaluate to true. Now, of course, here's the classic ones that always used to trip me up as a kid, but the important thing to remember is that we read from left to right, and so you look at what's on the left side of the comparator. So the left side is larger, so that means the left side of this evaluation should be greater than the right side, or x should be greater than y. And similarly right here, the x is smaller, so that means x should be less than y, in which case that will be equal to true. Now there's also slight variations on this I haven't mentioned here, but you can also do less than or equal to or greater than and equal to in Python as well. In is used for a membership inside a set, and so that can be either just a set as we saw earlier, with the Muppets, Kermit, Fozzie, and Piggy, or it can be any kind of set-like object. So dictionary keys would be set-like. So you can ask, is something in the keys of a dictionary? And finally, is used to check if two labels point to the same variable. Now, I have an example of this below, so we'll unpack this there. But beforehand, it's just to bear in mind, we can have two variables, A and B, and we can have them both equal to 42, but if they're not actually pointing to the same place in memory, while they will say x equals 42, it won't be the case that x is the same as y or A is the same as B. And we'll see that down below. Okay, so this right here has code whereby what's in the print should clarify the code itself. So we'll do that, and then we'll look back up top. So I'm just going to run this here. We'll say, x is yes. Then we have a thing here called xlist, which has yes, no, and maybe. And they're strings, you can see, because they got these quotes on them. So we'll say x in xlist, true. Yes is in this list of these three elements right here. Now we could say, does xlist equals yes, no, and maybe? And you notice here I have these quotes. It doesn't really matter if you have the quotes, because the quotes aren't really of concern. They just signal a string. So I know I use double quotes in all the instances, so let's just see what happens if I put the single quotes there. It's the same thing. It evaluates to true because it has elements with the same values in them. But on the other hand, have a look at this here. Xlist is this right here, and that's false. And that's because if you change something in X, you're not going to change something in this second yes, no, or maybe. So that means that even though they evaluate to be the same, they're not actually the same element in memory. What could be the same element in memory? Well, look at this. We make another list called ylist. We say ylist equals xlist. So now if I print ylist is xlist, and the answer is true. Now what that means is that if you change something in xlist, you will also change something in ylist. So we can see that down here. xlist.pop, and then print ylist. So what this should do is remove the last element of the list, which I believe is maybe, and then when we print ylist, it should also just print, just yes and no. It shouldn't print the maybe. And so check that out. And that's because, ylist is xlist. Now, strictly speaking, what we saw above were not actually elements of flow control. They were just ways in which we evaluate something as true or false. Now, where we would consider that as flow control is that we use if statements or if or else statements in order to direct what's happening in the program. So we use these sort of Boolean elements here, such as these comparisons, and indeed there's lots of others that we'll see as you go through programming in different ways, functions that return true or false and so forth. But what we do with them is that we then try to say, under this condition, if this is true, then do something, otherwise do something else. So here we have a pretty straightforward one right here. First I assign x to 5, and then we compare it. Say, is x equal to 5? And it says, yes, x did equal 5, thank golly. So of course we don't just have a positive condition, but we can have a negative condition as well. So imagine if x didn't equal 5, or in this case, if x didn't equal 6, well, there nothing is going to happen. But down below you can see we can use an else statement. So I put the else statement here inside a little coin flip. So this is also an opportunity for us to see something else. In this case, it's called a library. Sometimes it's called a package, and that's because packages can package up libraries or a module, because a library can contain modules. But in all cases, we have this import, and then we have an object. And so the object here is the random class. So the random class has some methods to it. Now, to reveal that a little bit more, you can see here if I import random, and then I go dir random, you can see that here are a whole series of methods. Again, we have these underscore ones here. We shouldn't really focus on those. Those tend to be for the system. And underneath we have an entire series of different ways to generate random numbers. You'll also see here that we have a thing called a seed. Now the seed is what sets the random numbers. So if you set the seed, every time you run the random number, you'll get the same outcome. So the computer generally produces a new seed every time you run random, but if you want to make sure that you get the same sort of pseudo-random number every time, you can set that seed. So in this case, what we're going to do is just use random in order to make a choice. So we have here a list I called coin sides. It has heads and it has tails. So I say if random.choice, so we're going to make one choice from these. If it equals heads, then we'll print you win. And if it's tails, we'll print sorry, better luck next time. So drum roll, please. All right, great, I won that time. So we can check that again. Oh, sorry, better luck next time, and so forth. And you can keep doing this over and over again, but you really are just going to get one of either of these two. And it should be almost exactly 50-50. And the longer you run this, the more it's likely to converge on 50-50. So now you might have more than two circumstances that you want to consider. In this case, we have heads and tails, but maybe you've seen a video or it happened yourself where, incredibly, the coin landed on its side. So it was neither heads nor tails. So that's not really very common in real life. But imagine that we suggest it's common for whatever reason, and we put rim in here as the third example. So we can say here, if side equals heads, if side equals tails, and then else, it landed on its side. What are the odds? So if we run this right here, once again, drum roll, let's see what happens. Sorry, better luck next time. I guess it landed on tails. Yeah, we can keep running this over and over again. It landed on its side. What are the odds? Well, here the odds are 1 in 3, it seems. Now you'll also notice that right down here, we didn't say else side equals rim. And that's because rim was the remainder of these options right here. So we've already got heads covered, we've already got tails covered, and so rim is covered by default. However, if we wanted to explicitly state rim, then we can also go, elif, side equals rim. Now that will have all of our bases covered, so we wouldn't really need an else statement for this. But imagine there could be another option, which is the coin vaporized. So we flipped it and instantly it disappeared. Now in that case, we might say, else print, where did it go? So it landed on its side. What are the odds? About 1/4. So where did it go? And indeed, that case, it chose vaporized. Now, the idea here is to point out that we can have many such if-else conditions inside this sort of conditional right here. You can go if, elif, and down and so forth. Now, it's not really the best programming pattern to be doing that, but it does work, although you may see more sophisticated programming patterns later on. The other thing worth noting is that what we don't do down here is go else if side equals rim. Watch what happens when I do that. And it'll have this colon there, it'll say expected. So why is that? And that's because after the else condition, we do expect a colon. So in this case, what it's doing is it's putting the if condition inside of this other one. And so in that case, we might see here, this will work the same way. And that should work. Sorry, better luck next time. Landed on its side. And indeed, it'll cover all those bases. All right, finally, we got one with where did it go? So you can see it does, in fact, go through all of those choices this way, but that's a bit messy. Now, the other thing that I want to point out right here, and this is the first time that it's really relevant within Python, and that is, you'll notice here we have a colon, and then we have this is spaced in, or we might say tabbed in, and says print you win. If I do this, then it's not going to work. It's going to throw an error. And you'll see the error says, expected an indented block after if statement on line 4. So we can carry that notion about being tabbed in, a little further. If we notice down here, with the else statement has this colon, so then we have an if statement that's tabbed in. Now notice that this is if side equals rim, print this, else colon print where did it go. So this is one set of statements, one set of if-else statements, because they're all on the same visual line right here. And this is another set because they're all on this line right here. You'll also notice that what I've done is I press the tab command to go in and out. However, in JupyterLab, and generally by convention in programming languages, if you press the tab command in, it doesn't actually use tab, which you can set to be 4 spaces or 8 spaces. It looks like tab, but actually it just ends up inserting 4 spaces within there. You'll also notice later on as you program, sometimes when you press the enter key and go down, it will assume where it is supposed to go based on where it is inside the program. So now if I press enter here, the cursor is not going to go back to the front. It's not even going to go back to here. The cursor should go on the next line just below print to suggest that we are inside this else condition right here. So just watch like this. And there we are. You can see, it's right there. Python is not common in computer languages for being able to do this. Most computer languages, you'll see, will have something like this, where we might have some braces or something that says this is what's happening inside the condition. And when you have that, then it might end up, it could be on the same line, or it could be the spaces don't really matter. But Python enforces that spacing as a way to sort of visually understand the program, as well as to syntactically be able to interpret where we are in these blocks. it cleans up a lot of parentheses, but at the same time, it also forces a kind of spatial convention so that it makes it very difficult to have like nested if else, if else, if else, because it will push itself along the page, and that can be hard to read. Now the next one that you're going to see here, and this is the walrus operator. This is a new one in Python, as of Python, I believe 3.8, might be 3.7, but it's pretty handy, and because you might encounter it, or I've certainly encountered it out there, it's worth considering. Now in order to establish which version of Python you're on, there's a couple different ways to do that, but you can do that right here in JupyterLab. So you notice above we imported a library called random. And so now we can import a different library called sys. And then if we go sys.version, you can see that I'm running Python 3.11, and it was compiled there at 8 in the morning on September 11th, 2023. Now that's not the date of today, that's the day that this was set. So because that's because that version works for this, and it's greater than 3.7 or 3.8, then it will the stuff down below will work. If you're on an earlier version of Python, well, I might suggest that you update your Python or update JupyterLab. You can do that from Anaconda Navigator if you're running in Anaconda. There's lots of tutorials online for how to update it, or just ignore this section. But for the rest of us, let's have a look down here at the walrus operator. So let's talk through the reasons why we might use the walrus operator. Now in the first example, I placed random.choice inside the if statement. So you see that up here. I said if random.choice coincides equals heads. Now I didn't do that in the second case. In the second case, you'll notice what I had done here is I made side equal. So I first created a variable, and then I did that down below. Now the reason why I did that is because if we were to put random choice in each of these conditions, random choice equals heads, elif random choice equals tails, because every time we run random choice, it's going to make another choice. That's going to keep this out of alignment. This time it might show up as heads and it prints you in, but if it might be tails. And then it goes down here, but it evaluates again. There's no guarantee that it's going to evaluate to tails. Now, if we want to condense this, so we have a way to not create a variable ahead of time, but create the variable right in the if statement, that's what the walrus operator does. Now, of course, it's called the walrus operator because it's like it has two eyes and these equals, which kind of look like tusks. So let's see it down in practice here. So let's see what I've done is I've assigned side to this right inside of the if statement. So we'll say side equals this random choice here, and then we'll evaluate whether this equals heads. So now in this case, coincides, you can see here it vaporized. This time it won. This time it landed on its side. What are the odds? And again, I'm winning. So this is pretty great. Now, you'll notice that I put these parentheses around here. Now, parentheses are really useful for directing the flow of an evaluation within an if statement. And that's because the if statement has itself some order of operations. So when it comes to the order operations in Python, these comparisons are done first and then assignments are done. So what happens now is it's going to say random choice coincides. It's going to do that. It's going to be one of our 4 choices above. And then it's going to equal, we're going to say, does it equal heads? True or false. So remember now we have 4 choices here, head, tails, rim, and vaporized. So in the case that it's heads, we'll still get you win. But in all of the other cases, it's going to go down and print side rather than print this stuff right here. So watch that. So false, false, false. All right, finally we got a you win. So indeed, it did work such that if the choice is heads, it will say you win, but the rest of them it just prints false because either it's going to be this case or in all the other cases, this is going to evaluate to false, so it's not going to work down here. By putting the parentheses inside, then what we're doing is we're saying first assign this to side and then go evaluate the rest of them. And now you can see it works just as we expected. Now in the section below, what we're going to do is compare to things other than Booleans. So that's certainly possible as well. We don't just compare to true and false, but we have things like empty strings and none variables. And so let's have a look at that. The first thing worth considering is that we can compare strings, and not just compare them in terms of equals, but also greater than or less than. Now, greater than or less than might trip you up a little bit because it's not the case that A is always less than B. We have a notion of a capital A and a lowercase a. Each one of those has, if you recall from the primitive data types, each one of these has kind of a point and a character map. So we have the large or the uppercase letters, then the lowercase, then a bunch of punctuation and so forth, and they keep on going down. So let's watch what happens when we do that with some strings. So you might say, is A greater than B? And then is capital A greater than B? And then is A greater than lowercase a greater than uppercase a? And then we have these results down here, drum roll. And so is A greater than B? No. But is uppercase A greater than B? No. Is lowercase a greater than uppercase a? Okay, true. So that's interesting. So you can see in the list of characters that if you were to print them all out, then you'll notice that first it's all the uppercase letters, then it's all the lowercase letters. So that means that the lowercase letters are going to have inside the computer a different character point and a greater character point. For the really curious among us, we can print that and print like so. And you notice the character point for A is 97, 65 is the character point for this. And so that's why both lowercase b and lowercase a are greater than uppercase a. So it's worth noting that helps us to be able to sort values within strings, but the sorting might not be what you expect. Now also with respect to things you might not expect, let's have a look at what also evaluates to false or true among numbers. So it says 0 is false, 1 is true, and the rest are trouble. So let's watch this down here. What evaluates to true? Now in this case, I didn't use a bunch of spaces. I did use a tab. And so the reason I use tab is because you'll see that makes it line up. This has a -1, this is a 0, 1, and 2, but the rest of these will all line up when we print them. So watch this. So you can see -1 evaluates to false, 0 to false, 1 to true, 2 to false. So you might think that if you're doing a comparison that you can put any number in there because they, only 1 is the one that evaluates to true. However, let's see, do they evaluate to false either? They don't evaluate to false either. So -1 neither is true in this condition, nor is true in this condition. So that means, -1 is going to be trouble. It means that 2 is going to be trouble. It neither evaluates to true or false. But on the other hand, you'll see here 1 evaluates to true, indeed, and 0 evaluates to false, indeed. So you can use 0 and 1 to set if-else conditions, but for the rest of the numbers, you should probably steer clear of trying to use them as equaling true or false. Now this here is perhaps a bit zen or reflective. It says, not everything that is empty is false. And there's a number of ways of expressing nothing in Python. So there's the notion of a variable being none. You can set none as a variable, or a variable could be empty. There's a numeric variable that isn't actually a number. It's called NaN for not a number. And then there's the empty string. So imagine we have a string, but we have no characters in it. So let's have a look at how some of these might work. Again, I'm going to import another package. In this case, it's NumPy. So NumPy refers to numerical Python. It's the basis of a lot of other Python libraries for data science, mathematics, statistics, and so forth. But itself is mainly concerned with distributions, matrices, and it has this not a number character within it. So we see np.nan. Does it equal true? Does it equal false? Neither of them. It's neither true nor false. Just like the rest of the numbers, it's trouble, except for 0 and 1, which are, false and true, respectively. So we say, if NP nan, and nan evaluates to true. Okay, so that means it is present as a number. Very confusing there. We can't say, we can't say that that's false. But down below here, you'll notice, hey, let's have a look at none rather than this. If none, none evaluates to false. Nan evaluates to true. Okay, so pretty confusing stuff here. Worth kind of revisiting this as you go along because it can be tricky. I'm not introducing it here under the assumption that you're going to kind of naturally embed this and be fluid with it. I myself have to often use little code snippets to test along the way. The reason I'm introducing this here is because we do often find a lot of missing variables in our data, and they can mess with our conditions if we don't know how to handle them or if we don't anticipate that to begin with. Now finally on that one, let's have a look at the empty string. And the empty quotes evaluate to false. So that concludes part 1 of this two-part chapter on conditionals, loops, and errors. In the second part, we'll cover the sections on iterations. So to start off this section, I give an example here of something that we might think of being easier to do by hand, but for which if we had to do it repeatedly, then it would get really tedious, and for which we could thus find a way to make that task automated, and we'll do that using iteration. So imagine having a file with a name like John Smith 131313.pdf. Not sure what this is. It could be like a user ID or something of that nature. Now imagine we wanted to sort by the user IDs. We don't want to go to a database and do something really complicated. We just want the files in our folder sorted by ID. So you can see here we already have some details about how we might do that and how you might do it yourself. By hand, you might go in and rename the file, copy this number right here, put it to the beginning, and put an underscore in front. So doing that with many, many files can get really tedious, but automating it is not that tricky. So here we have an example of a bunch of these things right here, this right here would be a little bit harder because, well, this number is in between the words, this number right here is in between them, and this one got really scrambled so that some ID stuff is within there. That would be a bit more of a complicated task, and it's harder to find ways to automate this because it's not regularly expressed. But this one up here, if we assume that there's always an underscore and then the IDs, then it can be pretty straightforward. So we have 3 records down here. This one right here, John Smith, Bernie Hogan, and Richard James. And so now if you'll notice, when we split and then we take the last element from our split, remember lists can either count forward or backwards, and we know that this will be the last one. So then we can print them. So it should print 1313, 113, 113, and then this number down here. Sure enough. So now you'll notice if we take this and go record.split, then we actually split in each of the sections. But now, how did it know that there was a record right here? Well, what happens is that if we have records as a collection, as a list, and then we go for record in records, then this will do that for each one of the elements. Now the word record is not important here. You'll see it's in black, so we can go print I.split, and it should do the same thing. And you'll often see I used within coding. However, personally, I prefer to try to find a more descriptive label so that we remember what it is that is the name for each element within the collection of elements. Also, it's like I said, it's the last one in the set. It's not like alphabetical or anything like that. So if we put another one in here, like so forth, and now if we do record.split, it splits the last one again within this collection. Now, as far as the last one goes, it's worth remembering that for a list, because it's ordered by position, the last one will be visually this last one here. But when it comes to dictionaries or sets, which one is the first and which one is the last might be a bit unpredictable. So you don't really want to guarantee, if you're using anything other than a list, that you'll be able to make use of the final element as being the final one that you added in the collection. Also worth noting is, just like with the if statement above, this loop right here has these sort of constraint based on position. So this is inside the loop, and this would be outside the loop. And so it'll print hello at the end. Now imagine if I put it in here, what do you think is going to happen? Well, we're going to print hello after each line, like so forth. And that's, again, visually a way that we can distinguish different parts of the program. This next little bit right here is just kind of a written version of what I was suggesting above around for loops. Now we can see, another example of here me using an iterator, for I in range 5, print I. Now sometimes you'll encounter an underscore instead of I. It's meant to signify that while we're iterating through a collection, we're not interested in each variable in the collection. We might just be interested in how many are there, or doing something for each variable, but not returning it. So we say here for counter equals 0, for underscore in this right here, print counter, and then counter plus equals 1. So you can see we're printing a counter, we're iterating it, increasing by 1 each time, and printing and so forth. However, it doesn't make sense for us to use underscore. We can use underscore as a variable, but when we see it there, it's meant to signify that we're not going to use a variable, but that's by convention. Now, a for loop also has an example of an else condition, which we don't see that often, but is another way of kind of finalizing things at the end of a for loop. And so it will always run at the end of a for loop. So for num in range 5, print num, else print done. So that means once we're completed all of this, then we'll do whatever's in the else condition, like so forth. Now, I say here maybe we'd be better called after or once finished or something like this, but it is called else within Python. Now, above you saw that I used a counter right here. And so we said we first initialize the counter, and then every time we go through the loop, we increment the counter by 1. And you'll see I've done that down here. Here's a list of fruit, apple, banana, cherry, and date. Initialize our counter and say, for fruit in list of fruit, print a tab, and so forth. So now we can see we've printed our counter, we've printed the fruit, the separator was a tab, so they're all nicely lined up. But imagine now, is there a simpler way for us to do this without first initializing a counter? And that's the enumerate function. And so it's pretty commonly used. And say so, for counter fruit in enumerate list of fruit. So you'll see now enumerate list of fruit will return not one value, apple, banana, cherry, but it'll return 2 values. It'll return a number starting with 0, and then whatever element was in the for loop. So watch this down below. Now, the enumerate function has an additional parameter start. So, we had it equals 0, but we can also say enumerate and start from 1 instead of doing the 1 plus counter above. And here we are. Ta-da! Now, why am I raising this now? It seems a bit tedious, but the important thing is that the enumerator is really useful for a counter. Now, I showed a little bit of this earlier in the video when we were or on primitive data types, when we were looking at modulus and integer division, and so we'll see that again here. So for C, num in enumerate range 30, so that means num is going to refer to 0 up to 29, and C is actually also going to refer to 0 up to 29. But now we're going to print the number every 5th time. So just watch this. 0, 5, and we don't print 30 because it didn't go up to 30. It went up to just before 30. So that way, if we started at 30 and then went on, it'll start from 30 and then go up to, 55. And as you can see, our counter is starting at 30, going up to 55, whereas the num itself is still the range that goes 0, 1, 2, 3, 4, 5, up to 30 there. So lots of ways in which you can flexibly use enumerate in order to help manage the flow through a for loop. Of course, it's not the only way to manage through a for loop. And there's two really important conditions that are worth considering. There's continue and break. Now, continue is about what happens. Let's say there is some sort of condition or other reasons why you don't want to do everything in the for loop all at once. You want to stop where you are and then go on to the next loop in the for loop. So it says continue from here. Go back and iterate from here. Break, on the other hand, just says stop here, finish the program, and then get out of the for loop. So let's watch these here down below. For fruit in fruits, if R in fruit continue, and then print. Now, I didn't use an else statement here. I just said if R in fruit continue. So we have a couple fruits here, and let's see. This one, what do we have? Cherry and a durian both have an R in them. And so, looking at this, I'm going to guess that we're going to print apple, we're going to print banana, and we're going to print eggplant, but we're not going to print the others. And look at that. The word apple is 5 characters long, 6 characters, but it did skip over cherry and banana because we used this continue statement right here. Now you'll notice down here what's going to happen if we say if R and fruit break, that means it's going to see the R and cherry, and it's going to say, oh, we're done. We're done with the for loop now. And so we didn't get as far as eggplant because we used break instead of continue. Now, the next few topics are a little more, perhaps a little more advanced as far as loops go, but they're also pretty common within Python, and they're worth highlighting. And the first one is a double loop. Now, let's have a look here. You can loop inside of a loop. It's useful for thinking about data in tabular form. Imagine you have a list of records, such as a person and their test results. So we have Alan, Barb, Carl, Dana, and Ella. And so we have test 1, test 2, test 3, and test 4. So the first loop might go through each row. And then the second loop go through each column per row. So that's the double in the double loop. And so I explained that down here with some examples, but now I've also put these scores in a list inside a list. So here we have 9689, 776. Are those those are the actual scores. And so watch what happens now as we iterate through the loop. Now in the first case, if we just do a single loop, we're going to print each row. And so we print that in turn. We could break it halfway through or whatever, but what we want to do is to just get the row. Now to get each element within the row, that's where we would have a second loop. So it says for row and results, but now in here we say for score in row, print the score. And then we'll have an end as a comma. And just to highlight that this is different, I'm going to put an ellipsis instead. And as you can see, for each one of them, it printed that, but it also added this extra dot ellipsis at the end. For what it's worth, imagine if we don't modify the end, and just did a default, what do you think is going to happen here? Well, it's going to print each number on a single line, and so it's going to have one long line, 16 lines long, 20 lines long, of the scores, like so forth, with an extra print in between. So, I was a bit fussy there, and I said I didn't like that trailing comma at the end. You'll see right here there's a trailing comma. So just watch what I do here in order to sweeten that up a little bit. So I say for score in row up to the last one, do this with an end, but otherwise just print the row, and then the end will also print a new line at the end of it. And there we can see now we've formatted those scores. We've been able to iterate through rows and then per row within columns. So it says we can work with this double loop in some interesting ways. if we want to calculate the average within row, that's not too hard. For each person, we can add up that person's scores and divide by the number of scores. We can call this student averages. But just to reassure you, it's not where we're going to stop with Python if you want to get an average. In fact, later on we'll have things like something like .average or .mean, depending on the program. But it is useful to see how we can do these things by hand. And so this is now when we start to get into some algorithms with for loops. So it says here, for student scores and results, I'm going to say total equals 0. And then for test and student scores, total plus equals test. And then student averages dot append total equals len divided by student scores. Okay, so just watch. It might be a bit tricky to follow. We're starting to get into some complicated code here. Okay, so what have we done? We've created the average per student. So the average for the first student was 8. Now let's go up and check that. Well, we can see they had 4 scores. 9, 6, 8, 9. That's 18, 24, 32. Yeah, so, this divided by 4 will equal 8 out of 10 probably. The one below is going to give us a kind of a longer number than that because it's going to be 27, which is prime. So, if you don't print it by, with the decimal points in there, you could get a really long number. But let's just watch this. So what we do is we have some total, and then for each column in this row, we're going to add to that total, and then we're going to divide by the number of elements in the total. So let's watch that here. For each student scores and results, so that's each row in results, we might say. We're going to start our total at 0, and you'll notice because it's in the for loop, that means we restarted at 0 for each row. Each student's score is going to start at 0. We're not going to add the other students' scores to this. That could get messed up. And it says, for test in student scores, total equals that. And then here, you'll notice where I've used the else, finishing the for loop. So first we add all the scores then, and once we're done the for loop, then we're going to first divide the total by the number of scores, and then add it to our student averages up here. And that's how we get the student averages below for student 1, 2, 3, 4, and 5. So let's see what happens if I just comment out this total so it doesn't do that. What's going to happen is that the total is going to keep increasing. And so this one is going to be that person's scores divided by 4. This one's going to be the total for the first 2 people divided by 4, for the first 3 people divided by 4, and so forth. So watch these scores just keep increasing. Yeah, and so that's pretty messed up there. In fact, didn't even start at 0 because we didn't initialize it to 0. If we did that, yeah, we're back to 0. But because we don't keep reinitializing 0, it's going to keep adding and adding. So to that end, it's important to remember where inside of your loops you're initializing variables. Do you want to have something outside, in which case it'll be initialized for the whole loop, or inside, which is going to be initialized just for that particular row or that particular element of the loop? Okay, so the double loop above was pretty straightforward because we first went by row and then did something within each row and got some number. But imagine if we wanted to go by column instead of by row. Now that can be a bit more tricky. We can do things in different programs to avoid that, and there's lots of ways that we can think about that in pandas or in a numpy array, but I think we can do it. We can manage without even going to these more sophisticated tools to go by column. But it's going to be a bit tricky, so I'm going to want to talk through this in a little bit of detail. If you can get this section, then you're really on your way in order to mastering loops within Python. Okay, so we have our entire code here. I'm going to run this, and it's going to give our test averages. So the average for the first test was 7.2, the next one was 7, and so forth. Now let's spot check that first before we go on. Now you'll notice here for test 1 we had 9, 7, 7, 8, and 5, and those all add up to 36. So we times 16, 21. 16, 23, 31, 36. 36 divided by 5 is 7.2. And, we can replicate that with the rest of them as well. So what we want this time is some way for us to get the averages for each test. And I'm going to do that down below by first making a new list that's the same length as the number of tests. So it's going to have 4 entries within it. And first I'm going to add Alan's scores. Then I'm going to add Barb's, then Carl's, and so forth till we get to the end. And then I'm going to take each one of those list entries, which is now going to have the total amount of marks, and divide that by the number of people who took the test. Okay, so here we are back down here. Now let's do that. Let's do that piecemeal first, just a little bit. So I'm going to run this code up top. Once I'm happy with this, then we're going to add code from this cell down below. So first of all, num students equals len results. So that means so far so good. That should be 5 students. Num tests equals len results 0. Now, it doesn't have to be 0, but we just want one element from our lists. Now that's assuming that this is a rectangle, and so later work we might not want to assume that, but in this case we're assuming that there is an entry in row 0 for each of the test results. So we should have num students equals 5, num tests equals 4. And sure enough, 5 students, 4 tests. So next up, this test totals and test averages. The test averages is going to be an empty list for now, but for test totals, what I'm going to do is I'm going to initialize it with a 0 for each one of the tests. So we're going to start at the scores are nothing, and then we're going to continue to add all of the people's scores for each of those tests in turn. So again, we can check that. Test totals is 0. Test averages is an empty one. And now we're on to our loop. So I'm going to add this up here to what we have above. Now I'm not going to add the else statement just yet. So I have the for loop here, and let's see what happens when we're done with this for loop right here. What are we going to have? So remember, test totals is going to be 0, 0, 0, 0. And then for student scores and results, what I'm going to do is add each one of the student scores to this. Now, how do I do it? One at a time. And I'm using enumerate in this case. So I have a counter, and then I have a test in enumerate student.scores. Now, just to clarify, we can print these. Print C, print test. That should work out all right. That's going to print a long list of, 20 rows. And it should have 0, 1, 2, 3 for the first person, then 0, 1, 2, 3 for the scores for the second person. There we are, 9, 6, 8, 9, 7, 7, 6. And this enumerate here, remember, it's going to keep reinitializing for every one of these inner for loops. So this is the 0th entry for the first row. This is the 0th entry for the second row. And you can cross-check that up here. All right, so we have these, and that's how we know if we go test totals, 0, 1, 2, or 3, it's going to look for, the first test total and add the test score, or the second test total and add the second test score. And just watch this. I'm going to print test totals as we go through the for loop. Oops. So you see we start off 9, 6, 8, 9. It's just the scores for the first person. Then we had all the scores for the second, then all the scores for the third, until we get to the end. So now at the end of our for loop, we're going to have test totals, and it's going to be this. That's the end. And then we're going to want to divide by the number of students. So this one we divide by 5, by 5, by 5, and then we get our test scores, which is what we'll see down below. So in order to do that, let's put the rest of this condition up in there. So remember here that the else is at the end of our for loop. So once we go through the for loop, then we do this. And now we're using another loop. So for each of the test totals, remember this one right here, we're going to create an average, and the average is going to be based on the total divided by the number of students. We had 5 students, and then we divide that total for each one of them and get our test averages. Run that, and then that's where our test average scores come from. So as you can see, it's a bit more tricky to go by column than it is to go by row in our double loop, but it's still entirely possible. If you can write something like this on your own in order to go by column rather than by row, like I said before, then you're really on your way to understanding these concepts and how to wield for loops as well as indexing within lists. Now, when we iterated through a list, we had a counter, and then we could index, using enumerate. So C will first be the 0th entry, then the second, then the third. However, for a dictionary, we tend not to use such counters because we don't iterate a dictionary by position. Now, as of Python 5, the native dictionary is a thing called an ordered dictionary. So it does mean that the order that you put them into the dictionary is the order that they should come out. But we can't guarantee that. And as we saw in the primitive section on sets, certainly if you iterate through a set, then there is no guarantee that the results are going to come out in the order that you added them. So with a dictionary, this right here is considered an item. That's a key and a value. So what happens when we iterate through a dictionary and we ask for something back? Are we going to get the items? No, we're going to get the keys of the dictionary. By default, when we iterate through a dictionary, it iterates through the keys of them. Salt, fat, acid, heat, just like above. Now, the reason that we do that is because we often want to check if a key is in a dictionary and then do something for it. So you'll notice that we had salt and Parmesan, fat and olive oil here. And now if we look below, if I print salt in ingredients and Parmesan in ingredients, what's going to happen? This will print true and this will print false. Now we know that Parmesan is in the ingredients, but it's in there as a value, not as a key. And so that's why it didn't evaluate here. Often we want to get the values though. So there's a couple ways that we can do that, and I'll show them below. So the first way to do that is that we can explicitly say for values. And now if we do this below, we'll see we'll get the values rather than the keys, Parmesan, olive oil, vinegar, toast. If we want to get the two of them together, you guessed it, it's an item. But now, if I print the item here, you'll see it's printing a tuple. It's printing the key and the value. So now that we have a tuple as that's returned from the iterator, we can in fact split that up in our for loop. So we can say for category food in ingredients.items rather than for food and then food 0 and food 1 or something a little more difficult than that. And so now you'll see category food in ingredients.items, and then I went with food.capitalize helps with the category. So Parmesan helps with the salt, olive oil helps with the fat, vinegar helps with the acid, and so forth. Now the next topic within iterations is one of my favorite sorts of syntax within Python. I remember probably about 15 years ago when I first saw this particular topic, list comprehensions, and I was delighted because it just seemed like it made a lot of sense. And in fact, as a bit of syntax, what I like about it is it actually reads almost like a sentence that we can do within Python. So a list comprehension is a way in which we can return a new list based on the old list. So just watch what we do down here. Here's how we might do it without a list comprehension. So here we have a list, and here we have a list of spices, allspice, basil, cumin. And then we have a new list. And then say for I in my list, so that's for each one of these, we'll first turn it into uppercase and then add it to the new list. So this should be within your reach so far. And you'll see what I've done here is we've all capped all of these. But this is kind of, there's a lot of code going on here that we probably could condense down into something we could condense down into something a little smaller. Now, if we go down here and see this as a list comprehension, just look at this. What we have here for these 4 lines of code, that's now condensed into one line. So here we say new list equals I.upper for I in my list. And you'll notice that it has the square brackets on either side of it. And so that's the list comprehension. Now just watch, it should do exactly the same thing. So the list comprehension was able to reduce the for loop down considerably. Now, these list comprehensions can be pretty complex, and I'm going to leave out much of that complexity for now, but one thing I would like to introduce here is how you can do conditionals within a list comprehension. The other thing I'd like to show is that you can actually do this and break it across multiple lines. So hopefully this will work. Now look at that. Now it is breaking across a bunch of lines, so I will just illustrate that here on a single line, which might help with readability. Or in fact, I'll do 2 lines here. Watch this. So the top part of the line is pretty much the same as what we had in here, but we don't end with the square bracket. Instead, we let it keep going and go, we'll do this if the length is equal to 5. So you notice allspice has 8 letters, basil and cumin have 5 letters each, and so it's only thus doing it for basil and cumin. So now if we can do this for a list comprehension, then perhaps we can also do it for a dictionary, and I'll show that down below. So they're pretty similar to a list, except whereas a list you just want one element for each part of the list, for each element in the list. For a dictionary, each element is an item that includes a key and a value. So you'll see I have this dictionary down here. I've put each item on its own line for readability, and then down here we have our dictionary comprehension. So I've done a couple little extra things in here as well. You'll notice I did this val.split 0 for key val. And why did I do that? Well, when we split by space. So this is going to show us how many measurements in teaspoons for each of these items. Now recall that with a dictionary, if we want to return both the key and the value, we would go dict.items. And so that can return either a single tuple, or it can return the elements within a tuple, which is what we've done with key and val. And then so for key.title, val.split this, in my dict.items. And really pay attention, notice that there's a colon in here that denotes the key and the value. And now let's print this below. So with measures in teaspoons, allspice, basil, and cumin. For what it's worth, if we wanted to have this as like a 0.5, make that an integer, that can get a bit tricky in terms of parsing fractions. They are coming down as strings. But the important part here is that we were able to iterate through a dictionary and then create a new dictionary with the old dictionary's elements right there as a dictionary comprehension. Similarly to a list comprehension, we can also do things like say, if, and then if something is the case, if it's greater than a teaspoon, or if the end is a teaspoon, or if the words have so many letters and so forth. But I'll leave that to you to explore and practice with dictionaries. So that's about as much as I'm going to want to cover for loops within this chapter, but loops wouldn't be complete without thinking about while loops. For a for loop, what we do is we iterate through all the elements, and when we get through the end of them, then we're done. We've got no more elements in our in the thing that we're iterating over. So we say for val in set of vals. However, with a while loop, this is used for times when we don't know how many things that we have to iterate through. There's a couple circumstances that are pretty common with this, and one, as we'll see below, is perhaps when we are using input for a person, and we want to say, keep asking for more input until you get the input that you're happy with. Before we do that, though, let's actually just look at a slightly simpler version with a break statement. So within this while loop right here, the first thing I've done is I've set some value to true. And then we're going to see while that value is true, it's going to keep doing things. Now, before you saw that we used the random library and we used random.choice, so we picked one value of a set of values. But in this case, we're going to do a random integer, and that's randint. Now, this randint is going to go between 0 and 10. Is it going to go up to and including 10, or is it going to go up to but not including 10? Well, shift tab here, we can see return a random integer in the range A and B, including both endpoints. So this is actually 11 numbers that we might end up seeing here. And then when I run this, I will, get some numbers. When you run it, you'll get some numbers. They might be different numbers. But in both cases, the last number is going to be 7. Why? Because if random number equals 7, we set x to false, and then we stop the while loop. So now let's have a look. So this one seems to be pretty long, lots of numbers there, but indeed it ends on 7. Run it again. 7 was the first number. We got lucky that time. Here we are. 7 was the 8th number, and so forth and so forth. Now, if you leave out the x equals false, which I wouldn't really recommend, then you'll see this run indefinitely. Now, I'm going to do that on my computer, just so you can see what happens. And I've moved my camera out of the way here because I want you to have a look up here at this dot. This dot is going to stay. It's going to stay black or dark, filled in until we break the program. How do we break the program? Well, let's have a look once we're in it. So I am going to comment all of that out, and it's going to keep printing numbers as it goes on. Now, the way it prints with this loop statement, it might get a bit odd. So I'm actually going to do something else in here first. I'm going to import time, and then I'm going to say time.sleep.5. And so that way, it's not going to just instantly print a huge amount of numbers. It's going to print one number every half a second, but it will still keep going until we stop it. And you'll see it just keeps going. We might even see a 7 along the way, and you'll notice that it will. We haven't got a 7, but if we do, it's not going to stop the program. It's just going to keep on going pretty much indefinitely. Gosh, no 7s here today. Imagine that. It took that long for us to get a 7, but that's because it is indeed a random luck of the draw. And, they just keep on going. So how do we stop this? You'll notice that this is still filled in, and down below it'll say the kernel is busy. In fact, you'll even notice that it's working on it right there. So the first thing we can do is just stop. And if we stop, scroll down to the bottom, you'll see it just said keyboard interrupt, and it just stopped the program. Now let's do that again. And another way to do that is that we can go up to the kernel right here and go interrupt kernel. And again, it's the same thing as pressing that stop. It's keyboard interrupt. You shouldn't have an infinite loop within your program, but in the case that you do, then you should be able to identify how to stop that. And once again, back to the classic. Okay, now here's an interesting use case for the while loop, and that's a chatbot. So just watch this. A value input equals, please type some text and hit enter, and then it says print, it appears you typed value. So if I, say, hey everyone, it appears you typed, hey everyone. Okay, so that's one input, we got the value, printed out the value. But now just watch this. We're going to put this inside of a while loop. And you'll see here, type y to leave the loop, type something else to stay. If value.lower equals y. So what that means is that I'm not fussy about whether we're going to print an uppercase y or a lowercase y, but if we print y, then we're going to say false. Otherwise, we're going to keep, going through the loop. So watch this. So, hey, I'm sorry, that's not a valid choice. What do you mean? And so forth. And it's almost like chatting with a very, very difficult chat GPT. But now just watch what happens when I print Y or enter Y. I've now exited the loop. And so you can see this is a way in which we can have something like from user input that keeps going until we get the wrong kind of, or the appropriate kind of input for exiting. What I also want you to notice is that while you're doing this, it's still busy because it's saying it's not calculating anything, but it is waiting for user input. So that means, let's say I want to run another cell. It's going to say cannot be executed due to pending input. If you find this in your program, you get that error. That means somewhere along the way, you have one of these input things that are open that you'll need to finish before you go on to the rest of your code. And now, of course, that's done. This is clear up here, and we can, type some more values. Now, the final section within this chapter is on errors. And so there we are. Below that, it's just the conclusion. So sometimes we want to raise an error. Sometimes we want to avoid an error, or rather, catch an error. And so let's see how we can do both of these below. So first, let's have an example of an error. 1 divided by 0, we know just from math that we can't do that. So it says 0 division error. Here is our 0 division error, and it just halted the program. Now in JupyterLab, because Jupyter is running on this kernel, it'll just halt this, but it won't clear everything out. It won't erase the memory, so we can adapt that, and it'll still run. But maybe we're either working with a script, and then once we get an error like this, it's going to stop the script, or maybe we want to anticipate this condition and then do something in the case that we have a 0 division error. So let's see how we might do that down below. Now I've again imported NumPy. I don't think it's really necessary to import it twice, but just in case you happen to be in this section without having imported things above, that's why I did that here. And now we'll see for I in the range -2 to 2. So now in this case, we'll see the range is range object start and stop, and it will go up to but not including the last number. So in that case, we should get -2, -1, 0, and 1. Now just watch what happens down here. I'm using a try and accept 0 division error. Okay, so it ran for 4 numbers. It didn't use the 2 here because it goes up to but not including. We could change that this way. When we have 1 divided by -2, -0.5, 1 divided by -1, but then 1 divided by 0 is an error. So we caught that error, and that's how we can manage the flow of the program by saying we anticipate this error. In that circumstance, do this instead. Now we might want to create our own errors for some reason, and we can do that using raise. So in this case, imagine we only want strings, or rather we don't want integers. So first I'm going to set x to be an integer, and I say if int x raise type error. So just watch this, and it's a type error, and then here is the explanation below, and that's what I put in there. You can see like so forth, and it will have that text in there. So now you may want to raise an error in your program at some point. Let's say you're parsing some files and a file is empty. So it might throw an error, or it might not throw an error. It might just continue parsing all the files. The empty one just has no data in it, but it's still a file, so it goes on. But you want to raise the error because you want to let the user know, hey, this file is empty. You should check your program. This program really shouldn't run with empty files. And so that's one way that you can do that. So now when we raise an error, it means we send an error to the program. This becomes a special kind of object that will usually end the program unless we accept it. So just watch down below another way in which we can manage this. And this is useful because sometimes there could be multiple versions of an error. Now we have 1 divided by 0, but we might have 1 divided by a string or something. And maybe you only want to catch one of them, but the other ones you want to make sure that you get feedback for what the error is. And so here is how, instead of just saying try except, which is what we had above, or except 0 division error, we can actually just make it quite neutral. In this case, we can say except exception, and that's quite general as error, and then print it, and then print the type of it. So you'll see first we printed the error, it's division by 0, and then we printed the name of the error. This is 0 division error. So that name is useful because that's the thing that we would put up here. So instead, imagine if we did this. The error is, this is the message, and it's a type error. So maybe we only want to catch type errors, but not 0 division errors. This way, we can learn what errors we get in the program and then build our exceptions accordingly. So for example, down here, I will just accept type error as ERR. Just watch that. It worked. We printed all this stuff. We know it's working. We can, print, hey, and that's great. But now if we do 0, then we didn't catch it because it's not a type error. So we got the classic Python thing down here with, with the red background that says that we're very much showing an error. Okay, so that concludes Chapter 4 on controlling the flow of a program. So a lot of new concepts, maybe a lot of neat concepts in there. Some of them are really important to kind of internalize and get used to, things like a for loop and a list comprehension. And some of them, like which characters, strings, or numbers evaluate to true or false, are important to bear in mind, but they are a bit of memory work, so it might take some practice for you to fully internalize them. They all are based on the notion of a Boolean, which is a variable or a value that will evaluate as either true or false. We can use those in if conditions and else and list comprehensions. So now this is a pretty sound basis for a program. In fact, with the skills that you have up to here, you can do just about any computation in a computer. Now that's pretty amazing to think about. It comes from the idea of a universal Turing machine. That's a pretty advanced concept. It's worth checking out, though, because it's a way of suggesting, can this language do everything needed for computation? So we have everything we need for computation right now in some respects, but that doesn't mean that we can actually get through everything we want in Python, because it's not just about the basics here. It's about how we make use of those basics with increasingly complex structures and increasingly complex data sources. In the next chapter, we're going to look at functions and classes, which is a way in which we can abstract on top of this and maybe create a little recipe or an instruction set for an ensemble or a set of these instructions that we want to do all at once. From functions, we start to see ways in which we can, optimize programs, reorganize them really effectively, and then really start building things that we're going to be able to use to, do our analysis. But that's it for this chapter. Thank you so much for watching.